Okay. So, hi everyone. Welcome to the 28th episode of the SFU Sports Analytics Virtual Seminar Series. Today we have Elijah Cavan, Brendan Kumagai, Riker Moreau, and Robin Ritchie speaking to us about punt returns using the math to find the path. It's a very clever title. So Elijah, Brendan, Riker, and Robin are all graduate students at Simon Fraser University. You can see their various supervisors listed there. So they're either master's or PhD students. As well, Robin is co-supervised by Dr. Alex LeBlanc at the U of Manitoba, and they all have a passion for sports analytics. In September, this group of students came together with the goal of conquering the Big Data Bowl, so that's the NFL's analytics competition, by developing new metrics, visualization tools, and ranking systems for punt returns. And as we've just been discussing, they made the top, we'll say the top 3, but maybe the top 8, depending on how you count it, out of 268 applications for the as a finalist. So that's just superb, and they're going to give us a preview of their talk today. So what their talk is going to cover is so this is for the 4th annual Big Data Bowl competition, and they're looking to construct an algorithm to determine the punt returner's optimal path instantaneously as the play progresses, conditional on the position of all players for that frame, and evaluate their decision making through traffic. In addition, they develop various metrics to evaluate returns and predict expected yards remaining for each punt return at every frame. Their main developed metric is an adaptive stochastic convex hull that quantifies field control for each team. They then evaluate punt returners' performances above expected and provide detailed rankings. So this sounds very, very appealing and interesting. So I will be quiet now and turn it over to the speakers. So thanks for joining us.
All right, hopefully everyone can see that fine.
Looks great.
Yes. All right, so thank you for having us today. We really appreciate the opportunity to share our hard work with everyone here. So today, once again, we're going to be talking about our entry into the NFL's Big Data Bowl competition. And our entry is titled Punt Returns Using the Math to Find the Path. So we'll start off by describing the Big Data Bowl competition and its goals. Our entry was split into 2 main parts. The first part aims to find the optimal path that the punt returner takes through traffic to maximize yards gained. This optimal path is also used to evaluate the punt returner's decision-making throughout the play. The second part focuses on modeling. In particular, we look to use new metrics to predict the expected yards remaining on a punt return at any frame. We will end with a quick discussion and answer any questions that you may have. So the Big Data Bowl is an annual competition, now in its 4th year. This year, the NFL challenged people to help evaluate special teams, which consists of punts, kickoffs, field goals, and extra points. They are looking for actionable, practical, and novel insights that use player tracking data. Their suggestions are to create new metrics, quantify special team strategy, or rank special teams players. 3 years of data is provided, including tracking and scouting data, as well as game, player, and play info. For our work, we are focusing on punt returns that resulted in a return from the 2018 to 2020 NFL seasons. Specifically, we include all frames from the moment the punt was received until the final event is complete, meaning a tackle, out of bounds, touchdown, fumble, etc. There are 8 winners that are chosen as finalists who will get to go present their work to the NFL. This year, we will get that chance as we were selected as one of the 3 college finalists, along with teams from MIT and Duke University. So here is a GIF provided to us by Zach Rogers' Big Data Bowl entry, which puts you in the shoes of the punt returner. The kick team players are shown in red and the return team are in blue. Using this, imagine that you're the punt returner and you just caught the ball, you choose to run it. Instantaneously, you must pick a direction in the hopes of gaining as many yards as possible while avoiding being tackled. Where are the safe windows in front of you that you can pass through? Where are your blockers? And where are the attackers that are going to reach you first? These are the aspects that of the punt return that we're looking to quantify by using the following methods. So we start by searching for windows between opponents that describe the potential openings that the punt returner may pass through. At each frame, new windows are formed and a new optimal path is determined. To do this, we use Delaunay triangulation, which is a mesh-like structure that connects points such that all players in the hull are connected to form triangles where no lines are overlapping. This is shown using the purple lines between any two red kick team players. And then finally, we adapt this by taking into account if the punt returner goes around all the players and towards the sidelines, we add new windows that connect the players on the outside of the hull to the boundaries of the zone of interest. And this is primarily shown with the vertical and horizontal purple lines.
All right, and once we have this defensive structure built out and we have the windows that this terrier can move through on his way towards the end zone, the next step we want to take is to create a metric to evaluate the level of pressure that the defense is imposing on any given point along these windows. So if you take a look at this plot here, this is our end goal for this step, where red represents areas of high pressure and green represents areas of low pressure. So as an example, if you take the window connecting number 79 to the sideline in the top left area there, you'll notice that right beside number 79, there's a lot of red there indicating that that he's putting a lot of pressure on that spot and he can be there at a moment's notice. Whereas as they move towards the sideline, you'll see it becomes yellow and then green, indicating that there's more open space there and that the carrier will have an easier time getting through that spot if he were in that area. And how do we actually calculate this? So if you can move on. Yeah, how do we actually calculate this heat map or build out this heat map? Well, we use our metric for penalized expected arrival time. And what we're doing here is we're basically creating an algorithm that's going to take in a target location on the field as represented by the X here. And we're going to compute the expected arrival time of every defender to that target location, penalized by all of the blockers in his path. And once we have this penalized expected arrival time for all of these defenders, we're simply just going to take the minimum time we expect the defender to get to that location. And that will be our measure of pressure at that point in the field, or the pressure that the defense is imposing on that point on the field. And now we'll take a look at a quick example about how we actually calculate this penalized expected arrival time. And for this example, we'll look at number 8 here in red and compute his expected arrival time to the target location X, with the blue players representing the blockers here. So in panel A here, we start off by calculating the blocker penalties. And the first step we have to do in doing this is to get a couple of measurements. So first, we're going to create a straight line that connects the defender with the target location. And we're going to project every defender onto this line and take the length of this projection. This is represented by D1 here, which is kind of like the lateral distance from the blocker, or can be thought of as the lateral distance from the defender. And we also take the distance from the defender to that projection as represented by D2 here, which can be thought of as the forward distance from the defender to the blocker. And using these two measurements, in panel B here, we're going to build out what we call a projected Gaussian kernel to get this blocker penalty. And this is visualized here by this diffusion style heat map and characterized by the function above. And basically what we're doing here is we're building a 1D Gaussian kernel where we set X to be equal to D1, or kind of the lateral distance from the defender's path. And we set the standard deviation to be equal to the forward distance from the defender's path, or D2. And then once we calculate the value of this kernel for a particular blocker, we're going to take the minimum of this value in 1 to kind of set an upper limit on what the penalty can be. And then we're going to multiply it by some constant K, where K is a bit of a tunable parameter. And in our case, we selected K to be equal to 5 after some trial and error and trying to find which value of K kind of looked best and best represented the blocker penalty and didn't kind of over or underemphasize it. In future work, we'd like to improve this a bit more by allowing K to be adaptable depending on the blocker or defender skill sets. And using this function, we get blocker penalties for each of them, or for each of the blockers on the field, and the time penalty they impose on the defender. And we can use that to calculate the penalized expected arrival time now. And we do this in 3 steps. So first, we tally up the blocker penalties. Here you can see we get 0.38 seconds in total for blocker number 40 and blocker number 95. Then we calculate the expected arrival time for the defender to the target if he were running at a straight line speed of 7 yards per second, and we get 2.81 seconds here. Then by adding these first two quantities together, we get our total penalized expected arrival time for player number 8, and that's 3.19 seconds. Then we can move on to repeat this process over and over for each defender on the field. And that allows us to get sort for the minimum penalized expected arrival time. In this case here, that's Tampa Bay number 33 with 2.02 seconds. And that's kind of our measure of pressure at that point in the window. And that's kind of where we're getting this heat map from. So we're just repeating this process over and over for up to 20 evenly spaced target locations along each of the windows. And then we get this nice heat map here that we desire from the beginning. And the reason why we chose to just do the heat map along the windows rather than building out the heat map for the entire field was mainly for computational purposes. So we have to repeat this process for every frame in every punt return in 3 seasons worth of data, which is very computationally heavy. And to be able to calculate or to run this algorithm for every point along the field, let's say like every XY coordinate or every integer XY coordinate on the field, it takes quite a while. So we're better off just doing it this way, and this kind of meshes a bit better with what Robin's going to talk about next in our A-star algorithm.
All right, so now that we have the windows determined and have associated an arrival time to each point along them, we look to pick the safest point in each window and, in a sense, connect the dots from one actionable zone to the next, where in the end, we will get a path like that shown here in black. To determine the optimal path through the windows, we adapt the A-star search algorithm to our context. The A-star search algorithm works by taking into account the cost of moving to a new point and the heuristic of how much closer does that move bring you to your goal. The algorithm works by finding the best path to the target by keeping track of the cost and heuristic totals and finding a new path whenever this total has become too large. For us, this path is meant to find the safest and most effective way to increase yards and get you to the end zone. Our heuristic function describes the remaining distance to travel to the target from a point, and here takes into account the yards remaining to the end zone so that we can gain as many yards as possible on the play, meaning that we take the difference between the punt returner's current yard line and the yard line of the end zone. For our cost function, we start by looking at all possible points along the nearby windows that the punt returner can go through from his given position. We then normalize the points along each window so that they are between 0 and 1, where 0 indicates a high penalized expected arrival time. This symbolizes a low pressure area by the defense and a safer point for the punt returner to pass through. A value of 1 would indicate a low penalized expected arrival time, meaning that a tackler can get to that point very fast. It's a high pressure area and a riskier point for the punt returner. From this, we add 0.5 to increase the weight of the normalized penalized expected arrival time term. And finally, we multiply this by the distance that the punt returner has to travel to get to that point of interest. The A-star search algorithm then does the work of verifying different paths and finding the one that gets the punt returner to the end zone in the safest and most effective way.
And once we have this optimal path, we want to compare it to the punt returner's actual observed path. And we do this by using Frichet distance, which is a measure of similarity between two paths. Intuitively, you can think of this as one path representing a man and the other representing his dog. And we want to find the minimum length of a leash that allows both the man and the dog to travel from one end of the path to the other while always moving forward. And that's going to be our value of the Frichet distance. So if you look at this plot here, this kind of gives an example about how we use Frichet distance. So we're just going to look over the next 5 yards here, as that best captures the punt returner's vision and decision-making at any given moment. And beyond 5 yards, really at that point, the play's kind of ever-changing. So at that point, the defenders and the blockers will all be in different locations. So we figured it would be kind of a nice little window to determine if he's making good choices or not. And if you look at the zigzags between the two curves here, these are kind of like discrete steps that we're taking along each of the path as chosen by the Frechet distance algorithm that minimizes the distance between these two curves as much as it can while taking kind of steps along each path. And if you notice there right at the end, there's kind of a light turquoise line there. And that represents kind of our final step, which also in this case ends up being the maximum distance between these two paths, which also corresponds to the minimum leash that would be required for both of these paths to travel across both of these paths while always being connected. And we have a couple of special cases here when we have less than 5 yards remaining. So when we have between 1 and 5 yards, we take the Frechet distance as we would before for these remaining yards. Then we're going to multiply it by 5 divided by the number of remaining yards to upweight for the fact that these two paths can only have like a limited amount of space to diverge compared to the full 5 yards that we get in every other case. So we're kind of dealing with that issue and making sure that it's not underestimated in that case. If there's less than 1 yard, then we just simply omit this from the calculation, mainly because at that point, the play is pretty much dead. And also, if we were to try the same process that we did for the 1 to 5 yard case, we would run into issues just with the numbers getting wonky since the remaining yards can be very, very small, meaning that it would be upweighted by quite a bit or be kind of over upweighted. And once we do this, we're going to take the Frechet path deviation for every frame we calculated on and just take the median value of this. And that's going to be our metric for Frechet path deviation, as we call it, or the difference between the observed path and the optimal path that we have in each play.
All right, so now to see it in action. In 2020, the New England Patriots punt returner Gunnar Olszewski completed an 80+ yard return for a touchdown against the Arizona Cardinals. Olszewski's path is shown in light gray, and the optimal path uses the black arrows. From the catch until Olszewski passes the final kick team player, the median Frechet path deviation is determined to be 1.904 yards. Our path is updated at each frame, and we can note that once the punt returner passes the final kick team player, we default to running in a straight line towards the end zone. A simple improvement could be to suggest an angled movement that goes towards the end zone, but away from the nearest kick team player, as to avoid being tackled even further. And once again, a punt return from the December 26, 2020 game between Detroit and Tampa Bay, where Jamal Agnew of the Detroit Lions completed a 74-yard return for a touchdown. Agnew's median path deviation is 1.906 yards. These paths suggest that Olszewski and Agnew are punt returners who often make good decisions and in a sense have good vision to take in their surroundings and quickly determine their movements such that they're going to increase yards and avoid tackles in a similar way that we're trying to quantify.
And now that we have this Frechet path deviation metric that can evaluate a player's decision-making and his ability to find open space and open seams on the field, the next thing we want to do is evaluate that metric itself by comparing it to the yards gained on the play. And we do this in this plot here where we have every single punt return in our data, and we compare the yards gained on that play with the Frechet path deviation here. And one thing that we notice is that when we're above around like 20 to 25 yards or so, we see that to get this far, you have to have a pretty low path deviation, or you have to be able to be making good decisions and to be finding that open space and open seams on the field to puncture through the defensive structure and get meaningful yardage. To put a concrete number on this, we observed a correlation of -0.44 between the Frechet path deviation and the log scale yards gained on the play. And that shows that there's a pretty strong relationship between these two variables. However, we do have to take this with a bit of a grain of salt because we didn't really do any analysis explicitly showing if there's causation one way or another between these two variables. So for example, what I mean by causation is like, is a low Frechet path deviation causing a high yards on play, or is a high yards on the play causing a low path deviation? But we kind of did use a couple of things, like I mentioned before with the Frechet distance, how we adjusted when we had less than 5 yards remaining to kind of maybe help deal with this or help avoid potentially potentially having cases where the yards on the play causes the per shade path deviation, which we don't want. And also beyond that too, really when we get above around 25 yards, usually at that point, the punt returner, if he gets that far, is going to be able to get by all of the defenders at that point. And at that point, we won't calculate the per shade distance since there's nothing to really calculate it on or no decisions to make since he's just running straight forward towards the end zone. So that's kind of a couple of ways we adjust for that. And we can kind of show here that per shade path deviation, we believe leads to more yards on the play.
Awesome. Now for part two, we focus on the evaluation of plays as a whole. So classically, we've seen metrics such as expected points added use the end yard line to determine a play's worth. So we aim to use a frame by frame approach with the end goal of estimating a metric called return yards above expected. So our goal is to use frame dependent features to predict end yard line estimates over every frame. The main metrics we use throughout our analysis are tackle probability, the adaptive stochastic convex hull, and the per shade path deviation that we developed in part one. So we developed preliminary features that were not only used in the optimal path algorithm, but also in our tackle probability model. The output from both of these models will be used as features along with the convex hull, and that will be used in a random forest conditional density estimate model, with the output being our return yards of expected, which we see as yards achieved minus the expected yards.
Awesome. So yeah, so as Riker was saying, most analysis was focused on between plays prediction. So predicting the yards gained for one play and then doing it for the next play. We want to focus on creating metrics for during play prediction. So within the play. So we want to create this in-play metric using continuous model, composed of discrete units, which are the frames captured by the tracking data. So there's two ways we might go about this. We might get point estimates at each frame. So that might be good, for example, for in-play prop betting. So we basically freeze the play at some frame and then ask how much farther will the returner might get and how much do you want to bet on that. We might also get a density estimate at each frame. So a density estimate would place a probabilistic weight on any number between 0 to 100, indicating the probability that the player returns the ball between 0 to 100 yards. So we can now ask questions like, what's the probability the returner gains X yards, and we can do that at each frame. So using either model, using either method, density estimate or a point estimate, our continuous model can now quantify the gain in expected yardage. So we can attribute credit to a successful party. So, i.e. we can quantify the gain in expected yardage due to a successful block or a juke or a missed tackle. We just have to figure out a way to label our data set to do that. So if you look at the plot on the right of this slide, you can see our continuous model for the tackle probability model, where a point estimate is made at each frame to describe the probability that the frame ends in a tackle. And what we can see is it does a good job at increasing as our frame number increases to 1 towards the end of the play. And we see it has an inverse relationship with the expected defender arrival time, which makes sense. If the defender is going to be there sooner, there's more probability that the player is going to be tackled.
So now we can look into tackle probability in more detail. So we used a GBM binary classifier with a twice repeated 5-fold cross-validation, while also upsampling our minority class. Our model was trained using 2018 and 2019 seasons, as we did for all of our models, and tested on the 2020 season. We filtered out plays that were not returned, such as fair catches or touchbacks. And I also filtered out fumbles, as they were very uncommon and did not follow our analysis. Some model features included leverages for blockers and defenders, defender distance, as well as the penalized expected defender arrival time. We determined blocking by looking at the closest blocker to each defender and determined a defender had to be within 2 yards of their blocker to be considered blocked. Looking at more details about how we calculated our main metrics in this model, all of these metrics are updated over every frame. So the defender distance is fairly straightforward. It's just the Euclidean distance of each defender to the returner. Blocker leverage, which was developed by Rumsey and Deflon in a previous big Dateable paper, was used to quantify the leverage of the blocker to disrupt the defender's play on the returner. So as we see in the figure here, we represent R as the returner, B as a blocker, and D as a defender. And then R plus is the predicted location of the returner after half a second or 5 frames. We predict this location with the speed and the direction of the returner. So we then measure the angles we represent as theta between the blocker, the defender, and the returner's expected position, and indicate that a smaller angle implies a more effective block. Next, defender leverage. So this is basically the opposite of the blocker leverage and quantifies the leverage of the defender to make a play on the returner. So this figure was taken directly from the Rumsey paper, where they used it on running backs instead of returners. So you can think of RB as R and RB star as R plus as in the previous slide. So for this leverage, we have to calculate 2 different angles. Theta 1 is the angle between the blocker, the defender, and the returner's current position. And theta 2 is the angle between the blocker, the defender, and the returner's expected position after that half second. So we calculate this angle as delta, which is the theta 2 minus theta 1, and interpret it as a positive delta implies that the defender position is improving as the returner moves, and a negative delta would mean that the defender position is becoming worse as the returner moves.
All right, so just some more specifics about the attack probability model. So the model tuning was done for us using the Caret package, so we didn't have to really worry about the tuning at all. But after grid search, we got an optimal loss function, or an ROC, which is used for binary classification of 0.88, with a sensitivity of 0.82 and a specificity of 0.74. We upsampled the minority class, so we got much better results. Prior to doing that, we got much worse results, obviously, because there's a lot of frames where there's no tackle. The optimal model has 50 trees and an interaction depth of 1, and the plot on the left is the output for 5-fold repeated cross-validation, with the optimal model being the blue line. On the right, we have the variable importance of this model. So you can see that the most important features are the distances from the closest defenders to the returner, which kind of makes sense, and then the arrival to the carrier, which we described in part 1, which also is clearly related from that first plot that we showed in part 2. And then some of our developed metrics, such as the blocker leverage and the defender leverage, they come next in the order of importance.
So now we can look at the adaptive stochastic convex hull, inspired by a paper written by Guan and Schwartz. So this is a way for us to quantify field position by each team during the return. So our novel contributions included making the hulls adaptive because it changes frame by frame, and stochastic because we remove defenders from the hull based on our blocking metrics. So if a defender is considered blocked, we no longer consider them a high threat to the returner. We only consider players between 5 yards behind and 25 yards in front of the returner, as represented by that green area on the right there. So in more detail, or to reiterate, the kicking team hull, shown in red, includes every player in that given green area that is not considered blocked. And the return team hull, shown in blue, includes all players in that green area. We calculate these areas over every frame and use this as a feature in a force conditional density estimate model that Eli is going to discuss next.
All right, so because we were training 2 different models, we were a little bit worried about data leakage or error leakage. So data leakage refers to a problem where information about the holdout data set, just the test or validation data set, is made available to the model in the training data set. So to prevent that for our case, we trained our tackle probability model using only the player tracking data and our developed metrics, i.e. the blocker or defender leverage. And the RFCDE model, or the random forest conditional density estimation model, uses the tackle probabilities outputted by that tackle probability model, the hull areas, so the kicking team hull and the return team hull at each frame, and the median path deviation at each frame to predict the distribution for the expected return yards, again, at each frame. The model specifics were an M-try of 1, so 1 variable at each split, testing at each split. The node size was 1 and the number of trees was 100. And we created this metric, RYAE, which is the actual return yardage minus a point estimate of the expected return yardage. Okay, so here we see an example where for a short return, so smaller than 20 yards, and our model does an excellent job of predicting the expected yards gain of the play. If you look at the loss function that's shown on the graph, it's often smaller than 3 yards. So our density estimates change as the number of frames increase, and naturally our model learns to get closer to 0 as the frame number increases. And again, this mean absolute error as our loss function is measured as the difference between the true yards remaining, which is that red dashed line, and our conditional point estimate, which is the purple line. Okay, so how do we get this point estimate? Well, an easy way would be to just use the conditional mean, the mode, or the median of the conditional density, and that's kind of what we did during the Big Data Bowl and what we submitted. But we found that a better estimate can be used by using like a conditional quantile. So for example, from the last play, that short return that we saw, what I did was I sampled from the 50th percentile, the median, and then I slowly started sampling from lower parts of the distribution as the frames increased. So at this fixed rate, I started sampling from lower parts of the distribution, and we saw that we got much better estimates for short and medium returns compared to some of the other point estimate models that I trained earlier on in the competition. Okay, so we saw we did pretty good for short and medium returns. This slide is kind of to show that we didn't do so good for the longer kind of returns like the Agnew play. So because most of our data set had shorter returns, our model isn't going to do great on long returns. If you look at during the start of the play, we're close to 20 or 30 yards off at some point. So to fix this, we could train a separate model specifically to measure large returns, or we could try to upsample this class of the data set. I would say that around frame 90, if you look, the model starts to place right here a lot more weight towards larger number of yards returned. It's just, again, it's too slow kind of learning. So again, it shows that if we had more data, maybe the model would learn to place more weight on more yards remaining in that return. Okay, so that kind of leads well to talking about limitations and future work for our modeling. So on the right, we see a little table which shows the relative loss function for various return length bins. So again, we see we get our best loss function when we have a short return. So that's kind of smaller than 20 yards. A medium return, which is like 20 to 30 yards, we do also pretty well. And then long returns, which are greater than 40 yards and extremely long returns greater than 60 yards, our model is kind of really, really poor. So what are some of the things we could do to improve our model? One might be that, we talk about the blocker leverage or the defending leverage. We don't consider double teams at all. So maybe including that into our analysis would help. Our tackle probabilities were ascribed to the whole frame. Maybe we could have ascribed them separately to each player, and maybe that gives us some, more accurate estimates. We could have used the player tracking data in the RFCDE model. I think that's one thing I would have redone if I could have redone the whole project, is just instead of training 2 separate models, just train one. Although the RFCDE model was a little bit buggy, to be honest. And we could have implemented the conditional density estimation with a more sophisticated package. And one thing we could have definitely done was, we put this probabilistic weight from 0 to 100 yards to project how many yards were remaining. Well, we could have done that 100 minus X, where X is the yard line where the punt returner catches the ball. So these are some ways that we could have improved our models and maybe gotten better results.
Awesome. So after the completion of our model, we used the results to rank all returners from the 2020 season. So we only accounted for players with at least 10 returns and ranked them based on their average return yards above expected over every frame. For reference, we also include NFL.com data, including each player's average return yards and their number of returns in the season. And then we also included the average path deviation from part 1 to determine whether the top ranked players followed our optimal paths. So here are the top 20 returners from the 2020 season. We see that players with the highest average return yards overall got good results from our model in the return yards of expected case. So usually the expected yards per play was close to 0 as long returns were uncommon, like Eli was saying. So the best returners likely had several chunk plays, as we can see with the top 3 players having a much larger return yards above expected, and even showing the touchdown plays from Olszewski and Agnew. So now looking a little bit more closely at our top players, Olszewski and Agnew, who we showed examples for, were 2 of the best players at following our optimal path. We see these players not only as highly skilled, but also as good decision makers. Deontay Spencer, who is our top ranked returner, deviated from our path more on average. So we view him as a player with high skill and natural talent, but he may lack the vision of our other players that I mentioned. I also want to draw your attention to number 14 ranked Jabril Peppers, who had the lowest path deviation. Although he did not have high return yards above expected, his actual average return yards was among the league best. We believe that his ability to follow the optimal path put him in positions to have high expected yards, in turn reducing his return yards above expected. After examining our submission a bit further, one thing I would have loved to change about these rankings would be to use the average return yards above expected over each play instead of the average for all the frames. I believe this would have given a better representation of performance, since this would have downweighted some of those rare long returns.
And just to reiterate a lot of what Riker just said, we can use these 2 metrics that we created in return yards above expected and the per-shade path deviation to both evaluate each punter's performance and find the driving factors behind this performance. So if you take a look at the plot here, we labeled the 4 corners where low path deviation corresponds to good decision-making and high path deviation to poor decision-making. And also high return yards above expected corresponds to high skill in terms of being able to dodge tackles and get by defenders. And low skill corresponds to low return yards above expected corresponds to low skill in the same area. And as you can see, as we had before, Gunnar Olszewski and Deontay Spencer are clearly number 1 and 2 in the league in terms of return yards above expected, neck and neck at 1 and 2. However, this doesn't really tell us too much about why they're good. And that's where the per-shade path deviation comes in, because that allows us to separate them. And we can see that Gunnar Olszewski has a very low per-shade path deviation, indicating that his success is generated by making good decisions and finding open space and open seams on the field, while Deontay Spencer has about a league average path deviation, indicating that his success, even though he's an okay decision maker, is probably more attributed to being able to evade tackles and slide by defenders while pressure is inevitable, or while he puts himself in tougher positions.
All right, so with all this, we look to answer, how is this useful to the NFL? First, we developed new and innovative metrics for evaluating special teams. We presented the adaptive stochastic convex hull, which helps quantify the control of the field around the punt returner while taking account of blocking. We use the penalized expected arrival time to estimate the arrival time of an opponent to any given position. We use the per-shade path deviation to quantify the decision-making of punt returners and how they face their current situation. Additionally, we created excellent visualization tools for post-play analysis, midweek film sessions, in-game feedback, and TV broadcasts. This is useful as we can then evaluate and discuss the decisions made by the punt returners and describe the situation they faced with various metrics and present it in a visual manner, which can help to improve the punt returner's ability. Finally, our optimal path algorithm can be adapted to any player moving towards a target location, such as the ball carrier moving towards the end zone, or even the gunner chasing down the punt returner.
So the next step in the Big Data Bowl competition as finalists is to create a short 5-minute presentation describing how one specific NFL team can implement our findings to improve their special teams. We have chosen the Kansas City Chiefs. As you may know, if you follow the NFL, Kansas City has a dynamic offense, which would only further benefit from better field position through effective punt returns. Mecole Hardman was Kansas City's main punt returner in the 2020 season. We aim to show how our work may help Hardman and the punt return team as a whole become more effective. Hardman's return yards above expected ranked 6th. However, he ranked outside the top 20 in average return yards among the returners in our rankings. We believe these results are due to his deviation from our optimal path, as he performed below average in this regard. We know that Hardman is a very skilled and elusive player who was an elite punt returner during his college days at Georgia. His high-ranking return yards above expected is likely due to a similar circumstance as Jabril Peppers, but is in the opposite sense. So Hardman's high deviation likely lowers his expected yards, but since he's a highly elusive and quick player, he performs well above expected. We believe our work would help the Kansas City Chiefs in a few ways. Kind of going over what Robin just said, coaches could utilize the algorithm to analyze returns and provide feedback during midweek film sessions. Players may also be able to get instant feedback via sideline tablets, which they could use to self-assess mistakes. And lastly, in a more general sense, management and coaches can evaluate any punt returner in the entire league. So to visualize our findings, we'll go through 2 separate returns from Hardman in the 2020 season. So on the left, Hardman does not follow our optimal path right from the get-go and chooses, in our eyes, a less successful overall route. On the right, Hardman's path deviation is much lower, and he is successful in obtaining a large chunk of yards given the situation. To talk a little bit more loosely about these 2 plays and think about it a little bit intuitively. In the left, we see that when Hardman decides to cut back left, our optimal path wants him to go to the right. As he does that, it seems like he gets hit by the player that our optimal path was trying to avoid. And then he ends up only gaining about a net of 1 or 2 yards in the play. Even if he would have followed our optimal path and only gained 2 or 3 more yards, our optimal path is there to maximize yards gain. So even if there was defensive coverage was really good after that point, he's still getting more yards than he got in this play. On the right, Hardman takes a more straight approach and follows the optimal path at the beginning of the return. Again, downfield coverage seems like it was really good as he gets swallowed up after about 10 or 12 yards. However, following that optimal path likely maximized these yards in a sense, and 10 to 12 would be a good return given the downfield coverage.
All right, so here are our references. Thank you for having us, and a special thanks to Tim, Tom, Alex, and Tyrell for their advice throughout this work. Are there any questions?
All right, great job. Thank you so much. Yeah, so let's open the floor for questions. Hopefully there's lots. So just feel free to either put in the chat or unmute yourself and ask. So while we're waiting, so I'm curious, like, I don't know much about football coaching, but like, how are punt returners coached, and like, what are the typical tactics utilized in pro football for these punt returns, and you know, how much are they practiced, and do you have any insights into any of the sort of nuts and bolts of how punt returns are coached?
I think that's a Riker question.
I'm not sure. I'm not sure. Again, I love football. I've been watching it for a long time, follow it like crazy, but I'm not sure how it's coached specifically. I do know that, you know, special teams coaches, you know, there's a specific coach for special teams that is someone who focuses on this as well as punts in general, field goals, etc. So I'm assuming, you know, someone like the Chiefs would practice this on a weekly basis. As well, someone like Hardman, who we looked into, was a returner in college and is becoming actually a really good receiver in the league as well. So usually this is, you know, a returner is someone with high skill set, elusive. You kind of see that across the NFL. So I'm not sure. I'm not sure exactly how they're practicing these types of things, but I know film is a big thing to do with downfield coverage, maybe not specifically to a returner's path like we're pointing out, but definitely downfield coverage and blocking schemes, etc.
To add on to that, just in terms of like strategy, like one thing Riker was, when we were doing the analysis for the next round, is he saw that there were a lot of like very conservative teams, like teams that were often, fair catching the ball and didn't want to return because they were afraid of, maybe getting a fumble or maybe, ending up back a few yards if the defender tries to cut back or something. So I think it is like, it is interesting to see like how they, use these kind of metrics that we're developing.
And sorry to chime into that as well. Riker also mentioned to me kind of earlier on in the competition too, that the returners are kind of taught to follow the blockers, right? So kind of like that's how you kind of try to find those seeds, is look for the blockers and look where they are, because they're going to be able to provide you coverage and area to get through. And that's something that we focused on in creating our arrival time metric. That's why we had that blocker penalty. That's part of the reason why we had that blocker penalty in there, and part of the reason why we kind of weighted it pretty high.
Interesting. So, maybe you touched on this and I totally missed it, but like, so is there a metric of like blocker effectiveness? Like you've talked about like the blocker penalty and whatnot. But like, so that's based on the spatial coordinates alone, but have you ever looked at film or actually looked at like, even if the blockers are in the right place, are they actually blocking the tacklers? Is that something like, can you comment on that?
Yeah, so for the sorry, I was just gonna say,
Brendan,
yeah, just for like our part, at least the expected arrival time part, we didn't really take that into account. That was a good point though, and something that we thought about. Just for this project, given the time frame we had, we didn't really have time to really separate. Like there could be two defenders like right beside each other, right, and then one blocker, and he's really only going to be able to take one of them. We didn't take that into account, which would be good future work, but yeah, that's a very good point there.
Yeah, going into a bit too, we did have we quantified the blocking leverage, and then as well, just like one of the limitations we had due to the double team blocking and stuff like that is we assigned every defender one return team player as like their blocker. So every defender had their closest blocker. That was the only person we considered for them to be blocked. And then, yeah, so we quantified it a bit, but like Brendan said, there's a lot more future work that we could have put in to details like that, that just with the timeline of the paper, didn't have time to look into.
Yeah, totally fair. Okay, Dr. Logan has his hand up.
Thanks a lot, team. This is fabulous work, and I just love being able to see dynamic graphics there, and that just brings everything you're doing to life. It's very well constructed and well arranged, and a lot of very interesting work. Good luck moving forward. I think this is a terrific entry. Okay, now the statistics part, starting from the obvious claim that all models are wrong. Your Fresh A model is wrong. Everything is wrong, but is it useful? And you of course are hoping that it's useful. But you also have hard data on punt returners, some of whom deviate from your optimal paths significantly and have outstanding results. Is there some way you might be able to use that information to improve your model instead of assuming that, well, they just got lucky, or they're just really highly skilled at avoiding being tackled? Maybe they're actually better than your model at finding a path through the defenders. And can you imagine a way that you might be able to update the model or improve the model? Maybe keeping the same structure, but you had to make a lot of simplifying assumptions through the process. Would there be some way maybe to use that information to improve your models?
I think personally,
oh yeah, sorry, you could go ahead.
I think personally what I would do is look at clustering the players based on their Fresh path deviations and other types of metrics, in terms of like kind of Brendan and Riker were saying, we were looking at the ranking. There are some players that kind of tend to follow the path better than others, so they shouldn't necessarily be penalized in terms of the RYAE metric that we're developing. So maybe finding some better relationship between the players would help us develop a better model.
Yeah, and to kind of add on to that a little bit, another thing that we were talking about yesterday, or when we were kind of choosing the chiefs for our final presentation, was that part of the reason why McCall Hardman kind of runs to the side a lot, or he kind of goes away from the optimal path, is because he's very small and quick. So what Riker kind of mentioned, and what I think too, is that he's always trying to go for the sideline and trying to just start and try to get up the sideline and just beat everyone with speed. So I think taking that into account, like taking in player speed, could be another way to improve the model as well. Like, because yeah, like a guy like McCall Hardman, who's very, very fast versus say someone else who's, I'm not sure, I don't have anyone off the top of my head, but someone who's not quite as fast, their optimal path should be a bit different, right? Since, like when you have that speed, you're going to be able to do more stuff, and you're better off maybe going to the outside a bit more, since you're going to have, it's basically going to be a race about whether you can beat that guy to the outside or not. Then building on top of that, maybe we can kind of go beyond that a little bit and use the results from Eli and Riker's tackle probability model to somehow incorporate that and actually really, rather than just assuming that they're highly skilled and they're able to slip by tackles, that like whether they're actually good at avoiding tackles when they're very close or not. So I haven't really thought too much about exactly how we would do that, but that's kind of, I guess, a future direction we could take.
Yeah, for sure. In addition, like our algorithm focuses primarily on the punt returner and not necessarily like the abilities of the individual blockers and tacklers. A good punt returner can have an amazing blocking team in front of him, and that can definitely contribute. So there's different like parameters in or constants that we put into our model that could eventually be adapted to incorporate those key players in front of them more, that might lead to increased yardage also.
I was also sort of wondering if there's some way to use trajectories of the individual players to update the model, because if I understand it, you're basically using their positions and then assuming that they have equal access to all 360 degrees around them and equal effectiveness in all 360 degrees around them. Whereas, obviously that's probably not right. It's hard to block somebody in back of you. And it's hard to tackle somebody in back of you. So yeah, I don't know if I don't know if the data is granular enough for you to figure out trajectories like that and be able to sort of use paths of the other players to help improve the model.
Yeah, if I could just jump in, like, do you consider the velocity, and again, sorry if I missed this, but like the velocities of the players, because I can imagine that the players are perceiving the rate of gap closing more than the gap distance at any given time.
That's certainly in like the tackle probability model.
Yeah, for our part, we didn't really take that into account like explicitly. Like we had the velocity in the data. We didn't actually add that in. Like part of the reason for, at least for defenders and blockers, was when we were building our expected arrival time metric, we wanted to kind of add in the directionality of the defender, then kind of project a little bit. So like, say the defender is moving kind of like to the right, or kind of like to my right here at like 5 yards per second, and then we would kind of project half a second into the future where he would be, to kind of quantify his reaction time and say where he's going to be before he's able to react and get towards that target location. But the reason why we omitted that for this was just because we kind of got an issue with the interaction between the defenders and the blockers, since we would have to do that for the blocker as well. And say I'm going straight forward as a defender and a blocker's coming straight at me. By doing this projection, we would kind of like flip them, where the defender would go straight through the blocker and the blocker would go straight through the defender. That's an area that we can kind of improve upon this as well, by incorporating that and maybe accounting for the fact that they can run into each other and that the blockers are really trying to stop the defenders. Then yeah, I guess we can use a similar approach as well with the punt returner to maybe move the target location a little bit for that, based on the punt returners, or yeah, based on the target location.
It definitely comes down to, this is tracking data and there's so much information at every frame of every second. Eventually it gets hard to incorporate everything and replicate a perfect play. So we definitely did make simplifications, but a lot of these like considerations would infinitely make our model better and could definitely be used for further improvement.
I think my team can correct me if I'm wrong in saying this as well, but I think the fact that the limitations from not including speed and whatnot are saved a bit from the fact that we're updating every frame, and every frame is like a 1/10 of a second. So like our path is updating every 1/10 of a second. It's taking into account, where these players are moving in that instantaneous moment. So yeah, so the velocity and acceleration, like people have been putting in the chat and stuff, would help. I think really help. But yeah, I think the fact that we use frame by frame aids us in when we didn't include those in the model.
Great. Okay, next question. So there's several people in line, just FYI for those who have your hands up. This is great though. Let's keep it going. Alon, you are next.
Hey guys, so first of all, awesome. This is really interesting and really great work. If you could go back to the part where you talked about why not incorporate the hull on the whole field, but limit to the kind of lines that you went with. So you said that you did that because it just computationally became too expensive to do it every frame. But on the other hand, you're recalculating kind of at every point, right? You're making this hull from scratch, whereas in consequent frames, it's obviously very similar to the previous frame, right? Is that fair to say that it doesn't change a lot from frame to frame? So could you possibly consider taking the previous frame's kind of hull into consideration when you're making the next one, so that you can have the entire field mapped, and that way you avoid some of the stuff that you showed, for example, the optimal path being a straight line once you run past defenders? That's because there's no lines going there, right? You're not calculating anything there. But if you had the whole pitch, then that would no longer be the optimal path. Is that fair to say?
Are you talking about the hull or the path?
No, so like before, if you go even maybe before the hull, even the
Robin, I think the one where
time. Sorry, yeah, this one.
One where Brendan was talking about, go back with the grid.
The heat map one.
The heat map one. If you go further back, the one where we talked about the computation time.
Yeah. So all of these
Yeah.
these graphs, you're obviously limited to the lines of the triangles and then the lines to the sidelines, which is one of the reasons why once you go past the last player, then it just kind of points in a straight line because there's nothing to avoid anymore.
Mm-hmm.
And you mentioned that you were limited by the computational complexity of doing this, but but these are obviously, this one and the next frame look very much similar, right?
Yeah.
They don't change by much.
Yeah.
No, yeah.
And so maybe you can leverage the similarity between frames to not have to start the calculation from scratch, and then maybe be able to do a bigger heat, maybe not a whole pitch, but a bigger heat map and a more detailed kind of thing, and improve it in that regard. Is that a fair thing to?
Yeah, I think that's fair. Like in terms of the heat map, part of the reason I didn't really mention it, the reason why we didn't do the full heat map is because we didn't really need it with the way we set up the A-star algorithm. And what would get kind of computationally heavier about that too would be that if we were to build out the full heat map and try to incorporate that full heat map into the A-star, then we would kind of have to move like step by step, like kind of meter or yard by yard, or however granularly we build the heat map. We would really just need these windows to use the A-star algorithm and choose like which window to go through. That's kind of the purpose of why we built out the heat map, so we can kind of move from window to window rather than kind of like step by step or yard by yard. But that I think there is an algorithm. There was a paper I saw about a week before we submitted where they had an efficient A-star algorithm for like continuous data or kind of semi-continuous data, where you have like a full out heat map, right? And you're kind of moving step by step. So like each yard you're kind of moving and finding your optimal path that way rather than kind of going to these discrete windows, right? But yeah, I think computationally, if we did want the full heat map, that would be a good way we can kind of interpolate over, say, like every second or couple of seconds rather than every 1/10 of a second.
Yeah, Lon, I think if you code the actual like creating the convex hull by hand, it'd probably be a lot faster than using a built-in package. Like then you reduce some of the computational costs.
Okay, thanks.
Next up is Dr. Swartz.
Hi, gang. That was terrific. Your talk incorporated so much content, and I was really impressed at how you looked at the literature and found algorithms and used these algorithms in your work. It was really great. The question that I was about to ask was sort of asked by Tom and then answered by Brendan. But I think when you give your big data bowl talk, there'll be tremendous interest in the practical stuff, the players themselves. And I really liked that that figure, which had performance on the vertical axis and deviation of the fresh A on the horizontal axis. Yeah, let's see.
Yeah, there. There we go.
Yeah, that one. I think that's great. And I think as has come up, you'll get questions about like Hardman. I was thinking about Hardman as soon as I saw this plot, and maybe get a real good handle on what's going on with him. So Brendan sort of answered it, but I think he goes sideways a lot, and I think he also kind of backs up and goes backwards. And so just knowing what's going on there will allow you to give a good answer to that question. But that's what I suspect is happening. He backs up and circles around, and maybe some other players do that too.
Yeah, we did. Brendan made up all of the GIFs that we had before about the optimal path, and we looked at all of his returns from 2020 when we were choosing teams. And one of the things, like you said, is he kind of like stutters at the beginning and then tries to run sideways to evade people with speed. And honestly, his results aren't great from it. And then the couple that we did see where he gained his most yards, he started forward sooner than he did with a lot of the ones where he gained 1 to 5 yards, even negative yards sometimes. So yeah, exactly.
Okay, thank you guys.
Awesome. Matt.
Hey team, great job on the project. I remember looking through a bunch of the big data bowl entries this year. I was actually surprised that this wasn't in the open category. I was very impressed with all the work that you guys were able to do and to carry on the SFU tradition of doing so much in so little time. So thank you everyone for sharing your project and for doing so much work here. I had some questions. One actually came up as there was a bit of discussion happening, and it was more about the concept of the optimal path. And the optimal path here was described as getting the most yards above expected. And I noticed in a lot of the recommended optimal paths, it's running through traffic. And there was a bit of a discussion about fumbling. So I was wondering if yards is going to be the appropriate value metric in evaluating this optimal path, because fumbling is like the worst thing you can do on special teams. And the optimal path consistently seems to suggest going into those high probability locations of where a fumble is most likely to occur, where you get hit by like 3 or 4 people at the same time. And I was wondering if you guys had tried using other value metrics, such as say expected points of an end line or something other than yards.
That's actually a very good point. I never even really thought about fumbling too much in this project or when we were creating this optimal path. But yeah, that's something that's very interesting and that we could kind of use in future work. One thing I will say though, when I was talking to Tyrell about this project, Tyrell brought up a very good point in what we can do in future work. And that's like, we kind of like, rather than use that, a bit of a Frankenstein function that we put together for the A-star algorithm for the cost function there, we can kind of look into more econometric stuff and look for like real cost functions. And then with that, if we're able to get kind of like a formal one that's, defined mathematically, we can also find one that is accompanied by a utility function. And the utility function will allow us to kind of adapt it depending on how much risk you want to take, right? So if you really don't want to fumble, you can kind of like lower the risk parameter and then get the optimal path from that. And then that would probably more likely suggest just going to the outside more likely than going up the middle, right? Whereas if you're willing to take more risk and maybe get more yardage, that would be something that you could up, then you're more likely to kind of go through. go through the middle and maybe get more yardage, but you're, like you mentioned, you'd be taking more of a risk at fumbling.
Yeah, to build on what Brendan said and what you said with the expected points added as well, I think we would have had to have looked, since we looked into returns only, a good way to look at the expected points added would be, if you add the risk, like Brendan was saying, have a cost function that incorporates the risk of a fumble, but then look at your optimal decision, which was actually, I think one of the other finalists did something similar to this, but the decision of, do I fair catch it? Do I let it bounce behind me? Do I try and return it? And then take the expected points added of like an optimal decision where we just focused on the when the ball carrier decided to make that decision to return the ball.
We could easily look at like frame one, what's the expected yardage or what's the expected points from our conditional density estimate model. And then, yeah, we could start to build out a decision model. I think that's an amazing question. It kind of builds more into the point of originally kind of what we were planning on doing is we borrowed from this Going Deep paper by Ron Yurko. And the idea is to, train a bunch of models that all like do, end up with one prediction. So we could have like a model that predicts fumbles and, have the ball carrier model that predicts how many yards remaining and then combine them all together to get exactly what you're saying. Like use a better loss function to describe, what's the best decision during a return.
One more thing to add, the A-star algorithm works by having a target. We defaulted to the end zone because that's in the end the ultimate goal, but an average punt return, right? We're only going to get 8 yards once you make that decision to run. So we could even lower the target and say, what's the best path to get you those 8 yards? And it probably would actually move along the sidelines much more often.
Fantastic. Great points. Thank you again for the wonderful project.
Great stuff. Thanks, Matt. Danny Chu.
Great job, everyone. Just like an immense amount of work and just really, really well done and really well presented and really clean and then statistically interesting. I think just all around an awesome project. And good luck in the finals. My question was something that I think Tom touched on it. I think I might have an answer based on your answer to Matt's question, but back on like comparing decisions, I was thinking like in Frichet distance, you could have possibly a good option to your left and a good option to the right and a bad option up the middle. And if you guys say optimal is left and they end up taking the right, you might penalize them a lot. Do you have any like indication that like if their path deviated from your optimal one, whether they were taking like a close to as good path just in a different direction? Is there some sort of like, again, cost function, which I think you said there wasn't, is there some sort of cost function associated with each path where you could compare them? Or maybe when there was a decision made and good results observed, maybe it was just like they broke a tackle or something and got a bunch of yards. Yeah, so I'm wondering, do you guys know when there was good results off of a different decision from your optimal one? Was it breaking tackle, or was it that possibly that other direction was just as good but a little bit worse than your optimal one, and so like it was still a good decision but you might be penalizing them a bunch?
Yeah, we didn't really take into account the possibility of like a second kind of optimal path or one that's pretty close to just as good. But one thing that we did to kind of combat if that were an issue was taking the median rather than the mean of the Frichet distance over all of the frames. And the way I kind of think about this is like, if you look at some plays, there will be an optimal path, say like you mentioned, one going right and one, then he's going left. Then there'll be a few frames where the optimal paths to the right, then eventually it'll just switch and kind of go his way to the left. So by taking the median, you kind of eliminate this like a large Frichet deviation for those few frames where that does happen.
Right, because it's adaptive.
Yeah.
Is that what you're saying?
Yeah. So
right,
it's like rerunning it every frame. Yeah,
gotcha.
and yeah, I kind of think about this a little bit like a GPS. Like when you're going somewhere with a GPS, or you have your maps app open up on your phone, and you're like trying to go somewhere, and it's telling you go this way, then eventually it'll just kind of go your way if you want to go a different direction. And you might kind of have a bit of a better intuition than the GPS, I guess, sometimes, right? Where you mean that route like 100 times, right? Then it'll kind of go your way at some point. So I guess that kind of gives a bit of room for carrier intuition, or for the returner's intuition to be built into it a little bit. And it doesn't penalize them quite as much by taking a different route from what we expect in a few frames.
Gotcha. I think my concern was totally not important considering I forgot like the adaptive part would just switch it. No, that's a really great explanation. That's really good.
Yeah, and
But I think too, Danny, like, oh, sorry.
No, go ahead.
I was just gonna say, like, I think you bring up a great point of like why we tried both approaches, because in that case, if a punt returner took not the optimal path and went the other way, but then still maybe broke a tackle and gained a bunch of yards, then they're gonna have a high return yards above expectation, but they're gonna have a very poor for shade path deviation. So they kind of like both methods kind of complement each other.
Yeah, that's exactly what I was going to say about that's when you see our high skilled players, in the sense that, you know, when they and that's why we use the path deviation in that random forest model, is that when they're deviating away from it, the expected yards drops, but then they make a high skilled play and gain more yards, and they get a really good return yards above expected, like Eli said. So yeah. Also, Danny, awesome thing you guys did with your you announced on Twitter yesterday with the scholarship. That's awesome stuff. Just wanted to bring that up.
Yeah, that was amazing.
And Lucas too.
All you guys, it was awesome stuff.
Right on. Okay, so we're at almost at 11:20. So I think now's a good time.
Dave, I apologize. I just
Yep.
want to ask somebody to give me more information so that I can forward that to my contact person, and that can get publicized too. So give me everything you got on it. Okay, I got a message from Robin yesterday, but tell me all you can, like all the details, and I'll pass that on. I apologize, Dave. I wanted to make sure I got that in before we went away.
Yeah, no problem.
Great, sounds good. I'm not sure about what the team thinks about this, but similar to the YouTube link for this video, I think just waiting for the finals to be done, just to
He's talking about more about the scholarship.
Oh, okay. Oh, sorry. I thought he was
do a quick plug of the scholarship so Tom knows what's going on.
Never mind. Awesome.
Okay, so I'm just going to shut the recording down, and then we can keep talking if people want to, and then to the extent that the team wants to hang out. Yeah, thank you so much for a really interesting and engaging talk. I think you guys got a great shot, you know, yeah, just wish you the best of luck in the competition.
Thank you.
Yeah, thanks for having us.
Great.